both are engineering students with an emphasis in civil engineering. On the left is Josh Boots, and on the right is Pavel Goski. The project was provided by BS Engineering, which is a local civil engineering firm. I'd especially like to thank the liaison, which is Brandon Durkle, sitting in the middle there. Brandon is a former graduate. He's been out about a year, doing very well at BS.
Okay, so good morning and welcome. This is the Roadway and Stormwater Infrastructure Project for our stormwater infrastructure design for Brownsburg Park. Brownsburg Park is located near Indianapolis. As you can see by the red space there, it's pretty obvious to see outlined by the circle. The scope of our project was to design the roadway and parking lot along to develop the grading plan for the site and to develop the stormwater infrastructure for the park. On the left is a picture of the existing terrain or the existing site. The site's about 700 feet wide by 1,000 foot long. It's about 16 acres. And on the right is an architectural rendering of what the site is to look like. There's a roadway that is to be planned for the park. For the roadway, we have to connect to the existing road that is going into the site, and then connect that road to the other road on the other side. There's a parking lot, about 15 spaces, that's to be for the park. And there's other activities that is planned by the architect to provide leisure and fun for the family. This area here is to be like a multi-sports complex or a multi-sport field that for the park.
Okay, so for the roadway design, we used AutoCAD Civil 3D to design a cross-section for the road, horizontal alignment, and a vertical profile for cut and fills of the roadway. So some of the design criteria we had to meet was we had to have 14-foot lanes on the roadway, which spans the road about 28 feet. We had 2-foot gutters, 5-foot sidewalks, and a 5-foot space between sidewalk and the roadway. We had a design speed of 40 miles per hour for this roadway. So here's a cross section of the roadway. At the top is just an artistic rendering of what we would actually see is the bottom part there. As you can see, we designed 14-foot lanes, and the sidewalks are also there. Also on the sides is just a cut and fill, which is basically bringing dirt in or taking dirt away as needed. Here's the horizontal alignment of the roadway. So this is basically like an aerial view of the roadway that we put in. The left connection there, that's actually a fixed connection. As Josh mentioned earlier, that's we're connecting to an existing road there. The right connection was up to us where to connect it. We kind of tried to follow the architect's layout. And there's 2 curves there, as you can see. The design speed's 40 miles an hour, but the speed limit posted there would be 20 miles an hour.
So this is the vertical profile of the road. It shows the elevation of the roadway as you go from the beginning to the end point of the road. Here's the crest of the roadway, or the high point that you would see, and over here's the low point, or the sag of our roadway. The sag point of the road is very important to us when designing the stormwater infrastructure, because that's where all the water will be collecting in a road. And the sag point's located about where the intersection would be going into the parking lot and following the roadway. Oh, too fast. Here's the pre-development model that was developed in AutoCAD Stormwater and Sanitary Analysis. The rainfall events that we simulated was a 2-year, 10-year, 25, and 100-year flood, and that was determined by the Indianapolis Stormwater Manual. There's 3 existing points on the site where the stormwater is leaving. They're designated by the red X showing the outfalls here, and this picture shows the watershed areas on the map. So, for example, the area outlined by the red line, all the water inside that area will be flowing to this outfall. And that's important to us when we're developing for the stormwater criteria for the site, which I will get to later. Here's the grading plan for the site. On the left is the existing topography, or the existing conditions, and on the right is the proposed elevations for our site. along with the detention basins. On the left, you can see how between the left and right pictures, you can see where the high points in the pictures have changed, where this would be a high point, and then that over here is the other high point. So the layout of the site was changed, which will change the watershed areas and where the water is flowing for our stormwater infrastructure design. So here's the post-development model of storm and sanitary analysis. It shows the different watershed areas and how the water is now traveling on the site. There's still only 3 existing outfalls leaving the site. So what we had to do for the stormwater infrastructure design is we had to meet the stormwater criteria given by the Indianapolis Stormwater Manual. So in those 3 outfalls, on the post-development site, the outfalls will be greater than on the existing site. So to handle the excess stormwater, you have to create normally the detention basin, which is like a pond or a lake, to hold the stormwater there before it leaves the site to slow it down. In our criteria, up here on the left is the detention basins, and for example, this criteria is saying Q represents the flow rate of the water, and the flow rate for a 2-year post-development has to be equal to half of the flow rate for the existing conditions or the existing site. So what this criteria is saying is not only do we have to meet the existing criteria on the site, but we have to improve the conditions. On the right, we have basically we have to design the inlets and culverts. We have to design the inlet for a 10-year flood and the culverts for a 25-year flood. And here's the equation for the water quality, which the water quality is to treat the first flush on the park. And the first flush is the first inch of rainfall, which normally carries the most pollutants, be it bacteria or cigarette butts. So you want to hold the first inch of rainfall, the first flush in the detention basin before it leaves the site in order for those pollutants to settle to the bottom before they leave the site and get into your stormwater. This is a picture of the soil conditions. We had 2 different soil types on our site. We had the Brookstone silty clay loam or the Crosby silt loam, but they had a dual hydraulic rating, which means the first letter of their rating was for drained conditions and the second letter was for undrained conditions. And soil was rated on a scale of A, B, C, or D, and A being for the best hydraulic soil and D being the poorest drained hydraulic soil. So what our site kind of has, this picture is showing us, is that we had mostly B, D, or C, D, or very poorly drained soil, which was going to make our stormwater infrastructure design a lot more difficult.
Okay, so here we have a kind of the area that we want to focus on in this presentation. So everything you see within that black line right there, any water that falls there will end up into the detention basin. And the detention basin is depicted there on the right. That's kind of the idea that we had in mind here. So basically, any water that would fall would end up in that proposed detention area right there in the blue circle there. The water would travel through pipes. We have pipes running from the parking lot, through the roadway, and some of the distances we're looking at like 250 feet going from the parking lot to the detention basin. Okay, so we have a pipe layout here. We have some of the pipe sizes here. We're looking at some pipe sizes going up to 20 inches. This is because sometimes during the 100-year flood, the parking lot will flood. And it's going to take a bigger pipe to manage a lot of that water. We have some slopes of about 2% for the pipes, and we got our elevations for our inlets, which is the table right next to it, from the vertical profile to put it on the roadway. And we did manage a 3-foot minimum cover for all of our pipes to keep them underground. Okay, so here on the right, you're seeing a profile view of the pipes. In the picture on the left there, in the green, that's the pipes that are being shown. So basically, if you just cut out a piece of the piece of the land right there, and you see the pipes exposed, you see that 20-inch pipe running from the parking lot to the detention basin, and those blue lines there show the hydraulic grade line, basically the water level, and our some of the design criteria we had was to keep that blue line at the crest of the pipe, which is the top of the pipe. And as you can see there, we did meet that criteria. So basically here, we just wanted to show what we were seeing in storm and sanitary analysis. This is kind of what we were working with. We have a culvert over there. I mean, you can't really tell what it is in this picture, but I will show you in the next few slides what it looks like. We also have stormwater inlets. So the stormwater inlets we designed for this project is a combination inlet. That's where the water will flow into to get into the pipe system and then eventually end up in a detention basin. Some of the design criteria we had to meet for the stormwater inlets was to keep one lane of the roadway unflooded, basically during a 100-year flood. So basically we needed to have 14 feet of roadway without any water on it. And after running our analysis, we did come up with a 4.29 foot spread on the roadway, which is how much it was going out from the inlet, so we had plenty of room left for cars to pass. So we have two culverts on our side. One's already existing. The one on the left is existing. We will be tying in our detention basin into that culvert to let the water exit the site. The culvert on the right is just kind of an idea of what we had in mind to put in under the roadway on the west connection to allow the water to flow to the northwest detention basin that was also proposed.
So we sized our detention basin using the TR55 method. The final volume of the detention basin was about 0.2 acre feet with a side slope of 3 to 1. The outlet structure is located on the far side of the detention basin in order to prevent short circuiting. Here's just a picture of our final model in storm and sanitary analysis, showing the outlet structure in our detention basin and all the previous stormwater infrastructure. Here's the outlet structure that was designed. We have an orifice which is the hole into the outlet structure of about 10 inches diameter. The height of the orifice is half a foot, which was determined by the stormwater quality, the water quality volume equation from the stormwater criteria previously. The total height is 3.5 foot, and the height of the weir is only 3.25 foot. So you can see this is the weir that we're talking about, is about 3 inches below the total top height of the elevation. The crest length is a foot, and the pipe leaving our outlet structure connecting to the culvert is about 20 inches. Here's the results that was determined from our final model. As you can see in the picture is our actual post-development flow rates and velocities meets the needed criteria on the left here. So the model was a success. And here's a cost analysis of the total project. The cost analysis was done using RS Means Building Construction Cost Data 2014. And as you can see, just the different quantities here in this column and the cost for each different task on the right. These are the only two tasks that was estimated not using the RS Means book and rates. This is the road and parking lot, the asphalt, on the project this was estimated using an online estimator. So you can see the different quantities for this is the roadway and the quantities for the parking lot with the following costs underneath. In conclusion, the proposed grading plan was created with the different elevations of the site. The roadway was designed and the stormwater infrastructure met the design criteria. We'd like to thank Dr. Jason Hill and Brandon Dirkholz again of BS Engineering, and also like to thank Shane Williams, who helped out a lot in the previous stages of our project, but for personal reasons was not able to continue on with this. Any questions? Brian Wilson.
Is your detention basin going to continuously hold water, or is it going to
Good question. That's involving the groundwater level of our site, which the groundwater level is not 100% known on our site. We're figuring that because of our soil conditions and the existing groundwater conditions, that it's going to be a wet detention basin and continuously hold a little bit of water throughout. Yes. Any more other questions?
I
Dr. Field?
actually had that same question, because then I was going to ask, did you have to give any thought to aeration of the detention basin, like a fountain, to keep it from going stagnant? That would be another.
That's a good question, Paul. I'll let Paul take this one. I don't think we went over the aeration of the detention
It's
basin.
not gonna be deep enough for whenever when it's wet, it won't be deep enough, I don't think, for fountain running. We're looking at 3 foot. When it's full, it's 3 feet, and it'll be draining.
Other questions? Okay, for your detention basin, does that parking lot drain? Is it part of what drains into the detention basin?
Yes.
Did you give any thought to having pervious concrete?
Yes.
Okay. Talk about that a little bit.
Kind of took that slide out, but we designed the roadway or the parking lot to have pervious pavement in the center for the. I'll show the picture of a parking lot here real quick. Unless we didn't put it on, okay. This the bubble here is in the parking lot is outlining the pervious pavement that we had designed for the park. We used different rates for the runoff coefficients and the Manning's number for the pervious pavement for the site. It decreased the amount of water that would be going to the detention basin. It infiltrated more water, so it helped. Because of the poor soil conditions on our site, it ended up helping out our model in the long run. So,
Okay, thank you.
if that answered your question, or if there's
Yep.
more other.
Do you want me to dig deeper?
Yes, you can. I'll try to answer all you got.
I think I'm good. Anybody else have questions?
So what did you guys do about the tension on the bottom compared to the side?
You're talking about for this detention basin here?
Okay, so you did design it.
Yeah, we're proposing a detention basin in the top left and a detention basin down in the bottom for the water running from the multi-sports field to collect down in the bottom of the site.
All right, let's give them a hand.